Good morning everybody. Today I am going to teach you about gravitational fields. So let's see what kind of fields that we can observe within the universe. We have main three fields that we can observe. So the first one is gravitational field, the second one is static electric field, and the third one is magnetic fields. I will list them there. The first one is gravitational fields. The second one is static electric field. The third one is magnetic fields. So the last two fields happen due to charges. The first one, the gravitational fields happen due to masses. In the second one and third one, the difference is the name is there. You can see in static electric field, the electric charges are not moving, but in here the magnetic electric field, electric charges are moving. But let's focus on our topic, that is the gravitational fields. So those fields happen due to masses. We all know the Earth can attract any mass into that body. So Newton is the great scientist who observed and discovered the gravitation. So he given a lot of knowledge beyond the story that we know about. So in here I will give you not the story but the knowledge that he given to the entire world. So we have main topics that need to cover in this lesson. So the first one is gravitational force. Gravitational force. Newton said that each two masses have their attractive force within them. These are action-reaction forces. These are internal forces. If you take the first one, let's take the mass as m1, the second one mass as m2. There is a same attraction force within those two bodies. So the forces are same, remember that. Although the masses are different, the forces are same. And we need this distance between the two masses. So Newton said that the force, the attractive force within these two masses are proportional to the two masses, and it is inversely proportional to the distance, inversely proportional to the square root of that distance. So we can take that the force attractive within these two masses are proportional to m1, m2 and inversely proportional to the square root of that distance. So we can replace this mark by with a constant. The constant is g. This is a universal gravitational constant g, m1 m2 over r square. So we have the first equation to measure the gravitational force within two masses. Actually there is a gravitation force within I will take example these two pens also, but we can't see they attack each other. So these two masses don't attract each other, and any other mass is attracted to the Earth. The reason is the value of g. This is a very tiny value. This is a very small value. The value of g is, I will list that here, 6.17 into 10 to the power minus 11. So it has a unit. We can take the unit by simply substitute this equation. The unit is Newton squared meter and kg minus 2. So this is the G value, the value of G, you can see the value of G is very small. So this is the reason the considerable there should be a if there should be a considerable force, the one of masses should be a very large value to overcome this capital G. So we then we have there should be a very huge mass to calculate the gravitational force. So that's why we are always discuss gravitational force relative to the some planet. So this is the equation we need to remind the calculate F value. So remember that the R is not the just the distance between two masses. We call them R is the distance between center of the masses. So remember that the R is the distance between center of the masses, because relative to the distance of these masses, the radius of this planet Earth and some another planet, we can neglect that value. So the R is too much bigger, so we are taking the center of masses, and we think that the every mass is concentrated to the center of that body. So that's why we are taking this center of mass, center of the distance between two masses. So this is the gravitational force. This is the formula for the gravitational force calculation. Then we are need to move to our second topic. The second topic is gravitational field. Gravitational field. There is a definition for that. The definition of gravitational field is the force acting on a unit mass. We call that the gravitational field. Actually, that's the strength of the field. We have a symbol for that. The symbol is simple G. Consider the definition. We can get the expression for that. The simple G is force acting on a unit of mass. So simple G equals to F over m. So we have a equation for Fm here. So we can substitute and take an expression for simple G. Let's substitute capital G m1 m2 over r squared, and let's again divided by m. So 1m is going to cancel out. Then we have expression for simple G is capital G m over r squared. This is a very similar to the equation for force. So in here we can take the unit as Newton, and here we can take the unit as Newton per kilogram, because it's defined like that. So these are the main two topics, topics that we need to study in the very basics of this lesson. So the next one is there's another very important topic to our physics, that's the energy. So in here in gravitational, there's also a energy calculations also. So you know calculation formulas. So in here also we have gravitational potential energy formulas. So the first topic is, then the third topic is the gravitational potential. Gravitational potential. There's also a definition for that. The definition is the matter from the infinity to some certain point of the gravitational field. If I think this is a mass having this is a planet having a mass of capital M and its radius is r. This is a infinity. So we are bringing unit mass, that means 1 kilogram mass, from infinity to some extreme point, some certain point of this gravitation. So gravitational field is also gravitational field is always an attractive force, attractive field. So it attracts the masses. So in here there should be a energy that is going to be supplied. Actually, you can under to supply an energy to this point, because it has always the attractive force. So the attractive force result to bring the unit mass to some certain point. Let's say take this distance as r1. So it is derived that the potential energy, that's not a potential energy, that's a gravitational potential, is minus capital G capital M over simple r. This is for the unit mass. So the units are joules per kilogram. So the final topic is gravitational potential energy. Remember that the whole lesson, the whole gravitational field lesson and calculation all are built up using these four theories. Every other things are application of gravitational field. So the last one is gravitational potential energy. Gravitational potential energy. So to the unit mass, so it's going to be any mass that is what we are bringing from the infinity. So we are taking that mass as simple m, and here we have capital M and its radius capital R. So we are bringing simple m to some certain point of this gravitation. So the distance that we are taking the particle is simple r. So potential energy is minus G capital M simple m over simple r. So it's very easy to compare these two. This is for unit mass, this is for any other mass. So in here the units are joule. If you think about this minus mark here, it's little interesting, because the potential energy or potential, can it be -1? So reason behind is we are taking the highest energy as 0. If any other energy smaller than that highest energy, that should be a -1. So I will take an example here. Think like this. You can easily understand if I take in this example. This is a planet. Let's take that's a Earth. If we have used to calculate potential energy using mgh, and there's another equation in this lesson. This is minus G capital M simple M over R. So these two are same. Remember that these two are same. This is for constant simple G, which has area as constant simple G. So this in here the simple G is changing. So that's why we are taking a full extended equation here. So this equation, when the H increases, the potential energy increases. So let's take here the value is 0. That's the surface level. Okay, then it's going to 100, 200, 300, 400 like this. But according to this equation, when the R is getting higher, the potential energy getting lower. But remember, there is a -1 in here. When H is increases, potential energy increases. So I'm taking infinity as the 0, because easily understand, if we substitute R by infinity, it is going to be a 0. So let's think like reverse. That means when we decreases R, potential energy increases with this minus mark. So if you decrease the radius or distance, the potential energy increases. So I'm taking this value as 100 relative to the infinity. okay, but there's a minus mark, so it's minus 100, it's minus 200, it's minus 300, like this. Then finally it's minus 400. So you can easily understand now this both two are same. In here relative to the surface or to the some extent point, the potential energy increases by 200. And here also you can understand relative to the surface to that same point, the potential energy increases by 200. So the same principle, the same scenario happening here, but the thing is we are taking two different positions to express our potential energy. In our thing, potential energy equals mgh to measure the potential energy. But in here, in our lesson, in here now, we need to take this equation. So this is the main 4 pillars that we are using to build up the entire lesson. So unheard application is going to build up. So this is the limit that I was planned to describe you today. So if you deeply understand these 4 theories, we can develop any application using these 4 theories. So I'm going to finish today work by now. So let's meet with another video. Thank you guys for watching.